We're getting into a new chapter that will talk about water and its important role in our environment, as well as its role as a solvent and other functions. So water has a lot of unique properties for a molecule of that size. These special properties is what makes water absolutely critical molecule for sustaining life on Earth. As you know, when we send mission to other planets, a lot of times the first thing is to find out if there is evidence of water in those planets. And the reason for that is because there's all of these different properties that make water unique for survival of life on Earth. So the first property that's important is the property of universal solvent. Water can dissolve a lot of different substances. We call substances that are dissolved in something else solutes. That's just a generic term. Solvent will be the substance that does the dissolving. High specific heat capacity, what this means is that it's able to absorb and retain a significant amount of heat before its temperature will go up. And this is not true for all substances. For example, if you compare water with sand, it takes only very little heat to increase the temperature of sand. Whereas for water, if you add that same amount of heat, the temperature of water will only increase by a little bit. This actually explains why desert environments have huge changes in temperature, either really hot or really cold, because as the heat is being gained or lost, that temperature change occur proportionally with the quantity of heat. Whereas with water, you can add a lot of heat or take away a lot of heat, the temperature will remain relatively constant. And that makes any place where there's a lot of water, that temperature in that area is fairly stable. The other property that's unique is the density anomaly. It turns out that liquid water actually has a higher density than ice. In other substances, the solid has a higher density than the liquid. The reason for the ability of liquid water to have higher density will be explained later when we talk about intermolecular forces. But this property is important because you can have frozen water on the top of a body of water, for example, like a lake or a pond, but the bottom part, which is where the pressure is higher, can still have liquid water because the density, which is higher at the bottom, allows liquid water to still form. And this is important because, of course, there's a lot of organisms that can only be alive if the water is liquid. If the water is solid, like ice, then all these organisms like fish and plants and stuff will also die during colder temperatures. Another important property of water associated similarly with that specific heat capacity is the high boiling point. It takes a lot of heat or energy to convert liquid water to steam or gas water. This makes it that water can absorb a large amount of heat when evaporating, which makes it an effective coolant. This is something we can see on ourselves when we do rigorous exercises or body sweats. The sweating is the conversion of liquid water to steam, and by sweating, we're cooling ourselves down and allowing us to be able to function even either in very hot temperature or while we're doing rigorous activities. The last properties that matter to us for water is these adhesive and cohesive properties. Adhesive properties allow water to stick to other substances, whereas cohesive properties or cohesion allows water to stick to itself. Both of these properties work together. So for example, water is able to go from the roots of plants all the way to the top, going against gravity. And the only reason that works is because water can pull itself up because of these cohesive property of water to stick to itself, but also that it's attracted to the wood and other polar substances that exist in the plant, and that allows itself to move up. That causes the plant to live because the leaves and other parts of the plant that's a lot higher requires water to maintain its life. A lot of these properties can be explained if we look at the three-dimensional structure of water or the molecular shape of water, which is something we've discussed in a past chapter. So water is what we call a polar molecule. Molecular polarity is just a measure of how electrons in a molecule is being distributed. So there's two different possibilities. We have either a polar or non-polar molecule. Here's an example of a molecule. And in the molecule, there's a lot of electrons. So for polar molecules, these electrons are distributed unevenly. So one side of the molecule has more electrons, the other side of the molecule has fewer electrons. We symbolize this side with this symbol called delta negative. And then on this side that has fewer electrons, we give it the symbol delta positive. And the reason it has negative and positive is because if you have more electrons, then you're going to be more negative. If you have fewer electrons, you're going to be more positive. These two positive negative ends of the molecule are like poles. So we call it, in fact, dipole because there's two poles in there. Anytime we have something like that, we would call the bond that's formed by these two atoms a polar bond. And since for this molecule HCl, there's only that one bond, the molecule itself is also polar. So you got to think about two things here. There's the bond polarity and there's the molecular polarity. A nonpolar bond is just where the electrons are distributed evenly. So you can see here there's not any part of this molecule where there's more electrons or fewer electrons. Because of that, we call it a nonpolar covalent bond. And since the only bond in this molecule is that bond, the molecule is also nonpolar. We have sort of the extreme case when we have an ionic bond where that electron is not just shared unevenly, but it's completely given away by one atom to the other atom, right? Forming these cations and anions, which you recall we discussed in a previous chapter. Now, why do molecules have different distribution of electrons? It turns out that depending on the type of element, there is a different ability of each of these elements to attract electrons. So it's really very much like a tug of war here. So if you're pulling on the electrons, some elements are stronger, so they can pull more of the electrons to themselves. Some elements are weaker, they can pull fewer electrons to itself. So overall, this side becomes positive and that side becomes negative. This property that allows an element to attract electron to itself in a covalent bond, it's called electronegativity. When we have a large difference in electronegativities of the two atoms, so if this one is really big and this one is really small in terms of its electronegativity, then the distribution of that electron is going to be really, really asymmetric. So most of the electrons will go to one side, very few will stay on the other side. We have a scale here that you can use to determine whether your bond is going to be polar or nonpolar. The way you do this is you just calculate the difference in electronegativity between the two atoms that are bonded. If the difference is 0.4 or smaller, then we call it a nonpolar covalent bond. Whereas if the difference is greater than 0.4 up till 2, then we call it a polar covalent bond. And if the difference is bigger, then we would designate it as an ionic bond. But right now we're just interested in these two types of bond. Okay, so we're going to take a look at how to determine whether a bond is polar or nonpolar on this question in the lecture notes. So we're going to look at a few different bonds here. And the steps are written right here. You first have to calculate delta En, which just means it's the difference in electronegativity values. And then the second part is to use that criteria I just mentioned to determine whether the bond is polar or nonpolar. For the electronegativity values, you can use this table that's on the left that shows specific numbers at the bottom. Those are the electronegativity values. So in this case, if we're dealing with CH, you would just take a look at the value for C, which is 2.5, and then for H, which is 2.1, and you subtract those two numbers. Sometimes students ask whether they should subtract one from the other or vice versa. My answer is always you just subtract them so that you get a positive number. So always use the bigger number first and the smaller number after. And so in this case, you get 0.4. Given the rule earlier, anything 0.4 or below is considered nonpolar, so we would say that this is a nonpolar bond. Now we go to CO. Hopefully this becomes easier. Carbon's 2.5, oxygen's 3.5. So again, take the difference so that you get a positive number, which is going to be 1, and 1 is greater than 0.4, so that's going to be a polar bond. Nitrogen, oxygen, we have 3.5 minus 3, which is 0.5. That's just bigger than 0.4, so that's also polar. OH, 3.5 and 2.1. Difference is 1.4, so that's also polar. And then carbon-carbon. Well, they're both 2.5, so if you subtract them, you get 0, which of course means it's nonpolar. As I said earlier, you need to understand both bond polarity as well as molecular polarity. And the reason they're different is because sometimes you have a molecule like water where you have two different bonds that exist. So the question becomes, if you have more than one bond, how do you determine whether the molecule is polar or nonpolar? it depends actually on which way these bond dipoles are pointing towards. So here I'm giving you two examples of two molecules. One is nonpolar, the other one is polar. One is carbon dioxide, the other one is water. And let me explain how we determine that polarity. So for a molecule like carbon dioxide, the Lewis structure looks like this, where there's carbon in the middle and it's double bonded to two oxygens. If you look at electronegativity values, which is shown right here, the oxygen is 3.5 and the carbon is 2.5, so the oxygen is stronger in attracting electrons. So this side of the molecule is going to be negative, and this side of the molecule is also going to be negative. So they're both pulling electrons. Because there's two opposite ends that are pulling on the electrons, these poles cancel each other out. In the end, you don't really get movement of electron. They end up canceling each other out. So what we say there is we say there's no net dipole moment and the molecule is nonpolar. Now here's a different example. Water, which has a bent structure, oxygen in the middle here, hydrogen outside. If you look at electronegativity, oxygen is 3.5, hydrogen is 2.1. So that bond is very polar between O and H. The polarity goes towards oxygen because oxygen is the more electronegative element. So a lot of electrons are located on this side. But as you can see here, the way that dipole is lined up is they're both pointing to the oxygen. So they're not going opposite each other, but they're both pointing to the same direction. As a result, when you add all of these together, it ends up giving you an overall molecular dipole that goes up towards the oxygen, where that side is negative and the bottom part is positive. So water is a very polar molecule, unlike carbon dioxide, which is nonpolar. You don't have to understand these arrow designations in order to be able to determine whether a molecule is polar or nonpolar. You need to use the following rules though. You need to first draw a Lewis structure, which we covered in chapter 3, and you need to remember the VSEPR molecular shape and electron geometry from chapter 4. So once you remember those, you can apply these rules. First, you check whether the bonds themselves are polar or nonpolar, and you can tell by using the electronegativity table and then this cutoffs for polar and nonpolar bonds. If the bonds are all nonpolar, then you just assume the molecule is nonpolar. If the bonds are polar, that's when things get a little bit more difficult, because you can have the situation like this on the left, CO2, or on the right, like water. So the way you tell is you checked the terminal atoms, which is the atoms on the outside. Remember, we have the central atom and we have the terminal atoms, which are the outside atoms. If there are no lone pairs on the central atom, then the molecule is nonpolar. However, if there are lone pairs on the central atom, then the molecule is polar. But this only applies if the terminal atoms are identical, right? So if, like this case, both oxygen on the terminal, no lone pair, that one is nonpolar. This one, on the other hand, water, if terminal atoms are identical and there are lone pairs, the molecule is polar. Now, the last possibility is if the bonds are polar and the terminal atoms are not the same, the molecule is going to be polar in that case. Okay, now we're going to do a few examples on determining molecular polarity. First, draw the Lewis structure, and then second step, you follow this flow chart. Now, the flow chart is based on those rules that I described in the lecture notes, but you're looking at three things here. The type of bonds, whether it's all nonpolar or it's a mixture of polar and nonpolar or all polar. And then you look at the type of terminal atoms, whether they're the same or different. And then lastly, you look at, do you have lone pairs or you don't? And you have to follow them in sequence like that. So we'll start with the structure of CO2. Carbon dioxide, we know how to draw the Lewis structure. It's shown right here. It has carbon in the middle with two double bonds to the oxygens. What kind of bonds are the carbon-oxygen bond? Go back to that electronegativity table and you'll find that the difference between those two is larger than 0.4, so it's going to be a polar bond. We're going to go to this flow chart on the right side, and then they're identical terminal atoms, so we're going to go on this one. Last is there is no lone pairs on the carbon, so then therefore the answer is this is a non-polar molecule. So hopefully that makes sense on how you apply that flowchart idea. So then we go to our next molecule, and H3 or ammonia. The Lewis structure is shown there with a lone pair on the nitrogen. Check the bond. NH happens to be a polar bond. We're going to go on the right side of this flowchart again. Terminal atoms are identical in this case. The nitrogen has lone pair, then it's going to be a polar molecule. I'm going to leave it up to you to think through the other two here, they're pretty much the same application of that concept with the flowchart. So hopefully you'll be able to see how I end up getting polar for the H2CO and non-polar for the C2H2, okay?